Hello everyone, welcome to this unit. In this video I am going to talk about the optimization of VASP performance and how we can make our DFT calculations faster by selecting the right number of cores. So by listening to this video, I will show you how to use your computer time allocation in the best way and increase the calculation speed in VASP. A frequent question that is always asked by VASP users many times is, for example, I have a cell with X number atoms and Y number electrons. How many compute nodes or cores should I choose for my simulation? This is a very typical question that is frequently asked. It's an important question because using too many cores is not always a way to speed up our calculations. And in many cases, applying too many cores will be inefficient, and the result is less of jobs completed in a given computer time allocation. That's why we need to learn how to optimize VASP performance by selecting the right number of cores in our different calculations. I have seen even many experienced VASP users apply only one scenario for all types of their calculations to make their calculations faster, which is not right and efficient, and they do not consider the parameters such as the number of K points and the number of bands. VASP currently offers parallelizations and data distribution over bands and over plane wave coefficients, in addition to parallelizations over K points. To obtain high efficiency on massively parallel systems or modern multi-core machines, it's strongly recommended to use all these parameters, technical parameters, at the same time. The important note that we need to consider is that we need to know our system and what we are going to calculate. For example, the way of optimizing VASP performance for lattice relaxation is completely different with band structure calculations with large number of K points. And the size of our systems, for example, the number of atoms and the number of bands, is very important and should be considered. So here I will talk about the different scenario of the VASP performance optimizations for different types of calculations. Before starting talking about how we can make our calculations faster, I need to say that there are some tags in VASP that you can apply to speed up your calculations, such as ALGO, LReal, and the mixing tags. But applying these tags are sometimes dependent on your system and what you are looking for, and these tags could affect your results. Therefore, working with these tags demand too much care, and if you don't pay attention to them, they can affect the accuracy of the results. For example, ALGO is for specifying the electronic minimization algorithm, which the default in VASP is Bloch-Davidson iteration scheme. And the second one, LReal, determines whether the projection operators are evaluated in real space or in reciprocal space, and is highly dependent on the size of the system. The real space projection scheme for systems containing more than 20 atoms is always recommended, and for a small system, reciprocal space is recommended. So in this video here, I'm not talking about these tags because it depends on what you are going to calculate and your system, and everyone should apply them with too much care based on the system in order to get the highest possible accuracy. Here I'm going to talk about how we can optimize our calculations without affecting the accuracy of our results. Now let's get started. The main rule of thumb for the right selection of the number of cores in our calculation that I always suggest is take the number of cores as the same number of atoms. This is almost always safe rule, and will not waste computer time, and typically it will ensure a parallel efficiency of at least 80%. This is a general rule without paying attention to other parameters in our system, such as the number of key points and the number of bands, and also the number of cores in one compute node in our cluster. For example, if you have 80 atoms in your system, taking 80 cores is generally the most efficient selection without thinking to any other technical parameters in the system. This is of course a very unscientific rule, but it's simple and easy to remember, and you don't need to consider any other technical parameters. In addition, general tags that can be used in in-car file are ncore and npar. And these two parameters are in a relation that ncore is equal to the number of cores per npar. We should either specify ncore or npar. That I always recommend ncore because it's kind of more straightforward. Ncore determines how many cores share the work on an individual orbital. Npar equals the compute nodes in our system, or ncore equals the number of cores per node. For example, if we want to apply 32 cores in our calculation and our cluster has 16 cores per node, it means we are applying 2 nodes. We need to set ncore equals to 16, which leads to applying 2 nodes for or npar equals to 2. But we need to set just one of these two tags in in-car file, ncore equals to 16 or npar equals to 2, that I suggest to use always ncore. Let's now look into how we could make a more accurate estimation by considering other technical parameters. VASP has 3 levels of parallelizations. The first one is our bands, which can be determined indirectly by the number of atoms and electrons in our system. The second one is our k-points, and the last one is our plane wave coefficients, or equivalently fast Fourier transforms. It's very important to ensure that when your work is split up over several compute nodes, there is a sufficient amount of work to allocate to each processor core. If, for example, you split up your work over 4 nodes and each node has 16 cores, but you could not allocate a sufficient amount of work to each processor core, they will just wasting time and waiting for more work to arrive. So the main parameter that we need to look up to escape from wasting computing time is, first one is the number of bands, which can be determined indirectly by the number of atoms and electrons in our system, and the second one is the number of k-points, and the last one is the size of the basis set, which is the number of plane waves, which corresponds to the number of grid points in the fast Fourier transforms. If we can estimate or derive these numbers for our calculation, we can more precisely guess a suitable number of cores to use. So let's start with the first parameter, that is the number of bands. The first step is to consider the number of bands, n bands. As I already said, VASP has parallelization over bands. The ultimate limit is 1 band per core. So if we have, for example, 500 bands in our system, we cannot apply more than 500 cores and expect it to work well. I have experienced this matter when I was working with a very big system, including almost 700 atoms and 4,500 bands. I didn't pay attention to this point, and I took more than 4,500 cores to speed up my calculations, but it didn't work at all. What I have seen in my scaling tests is that 1 band per core is too little work for a modern processor. So you need to have at least 2 bands per core to reach more than 50% efficiency. Of course, a conservative choice is 8 bands per core that will give you closer to 90% efficiency. So how does this relate to the rule of thumb that I said before? By apply it, you will arrive at a number of bands per core equal to the average number of valence electrons per atom in your calculation. If we assume that the typical VASP calculation has about 4 to 8 valence electrons per atom, this will provide 4 to 8 bands per core, which is usually okay. So to sum up, we can consider that the number of cores can be equal the number of bands divided to 8, 6, or 4. Let's give an example to illustrate this point. Let's consider we have a cell with 750 bands and a cluster with compute nodes having 16 cores per node. We aim for 8 bands per core, which unfortunately means 93.75 cores. It's better to have even numbers for the number of cores, so we increase the number of bands to 768 by setting n bands equal to 768 in the incar file and allocate 96 cores, which is equal to 6 nodes. Suppose that you want to speed up the calculation in the previous example. You need the results fast and care less about efficiency in terms of the number of core hours spent. You could drop down to 1 band per core. That means you need to use 768 cores, that is equal to 48 nodes. But there is really not too much improvement compared to 2 bands per core, 384 cores. So it seems like 384 cores is the maximum number possible. But what you can do is to take these 384 MPI process and spread them out over more compute nodes. This will improve the memory bandwidth available to each MPI process, which usually speed things up. So you can try running on 48 nodes but using 8 cores per node instead. It could be faster if the extra communication overhead is not too large. The next step is to consider the number of K points. It's very important when you are dealing with the system with a large number of K points, for example, for the band structure calculations. VASP can treat each K point independently. The number of K point groups that run in parallel is controlled by the K-par parameter in incar file. The upper limit of K-par is obviously the number of K points in your calculation. In theory, maximum number of cores you can run on using combined K point and band parallelization is n bands times K-par. For example, 1000 bands and 10 K points would allow up to 10,000 cores in principle. However, in practice, K-point parallelization does not scale that well. What I have found is that applying K-par equals to compute nodes usually allows you to run twice as many cores as you determine in the previous step, regardless of the actual value of K-par. I would not recommend attempting run with K-par more than compute nodes, even though you may have more K points than compute nodes. I will make this point more clear by an example. Let me explain with an example. Consider our previous system including 768 bands. We showed that 96 core was a good choice when using just band parallelization. But just consider that we also have 12 K points. So we can set k par to 12 and double the number of cores to 192 cores or 12 compute nodes. In this case, we end up with 1 k point per node, which is a very balanced setup. Note that this may increase the required memory per compute node as k-point parallelization replicates a lot of data inside each k-point group. If we would run out of memory, the next step would be to trying for lower k-par to, for example, 6. The last step is considering the size of basis set, L-plane, and NGZ. It might be worth considering what the load balancing of your fast Fourier transforms will look like. VASP by default works with fast Fourier transforms in a plane-wise manner, meaning L-plane equals true, which reduces the amount of communication needed between MPI ranks. In general, we want to use this feature as it's typically faster. The three-dimensional fast Fourier transforms are split up into two-dimensional planes, where each group, as determined by n-core, works on a number of planes. It means that ideally we want NGZ, which is the number of grid points in the z direction, to be evenly divisible by n-core in the in-car file. That will ensure good load balance. We need to consider that NGZ, the number of grid points in the z direction, should be sufficiently big for the L-plane approach to work. It means that NGZ should be more than 3 times n-core. So this threshold is very important for us, and we always should pay attention to that, and always NGZ should be more than 3 times n-core in our system. Typically for larger systems, normally with more than 100 atoms, NGZ is usually larger than this threshold. So there will be no problem in this regard, as long as we stick to the rule of using n-par equals the number of compute nodes, or n-core equals the number of core per nodes. But we should still check that NGZ is an even number and not, for example, a prime number. We can also tune NGZ in our calculations. In order to tune NGZ, we have two choices. The first choice is that we can adjust the cutoff energy for the plane wave basis set to a more appropriate number and let VASP recalculate the values of NGX, NGY, and NGZ. Second, we can switch from specifying the basis set size in terms of an energy cutoff and set these parameters, NGZ and NGX and NGY parameters, directly in the in-car file instead. Well, but for a very small systems with NGZ falling below this threshold, it means that for very small systems the number of grid points in the z direction is less than the 3 times n-cores in our system. We can also consider lowering the number of cores per node and adjusting n-core accordingly. So, for example, we can apply n-core equal to 12 or 10 to just fulfill this threshold in small systems. Just to sum up what I have said in this video about how we can improve our VASP calculations by selecting the right number of cores. The first step is the main rule of thumb for the right selection of the number of cores in our system, which is taking the number of cores as the same number of atoms in our system. This is a very general rule without paying attention to other technical parameters. Of course, it's not very scientific way, but it's very easy and straightforward to remember. For more scientific way, we need to check the number of bands, n bands, in our system. This is typically important for the cases with a large number of bands, for example, large system including a large number of bands. The number of bands divided by 8 is a good starting guess for the number of cores to employ in our calculation. If we are dealing with more than one K point, we can set K par to the number of compute nodes or the number of K points, whichever is the smallest number. Then double the number of cores determined in the previous steps, step number 2. The last step is regarding the ngz, the number of grid points in the z direction. We need to make a test run and check the value of ngz. It should be an even number and sufficiently big, larger than 3 times core per node. For larger systems, typically with more than 100 atoms, ngz is always larger than this threshold, so there will be no problem in this regard. For a very small system, with ngz falling below this threshold, we can also consider lowering the number of cores per node and adjusting n core accordingly. Adjust either the basis set size or the number of core per nodes. I would like to thank you for listening to this video, and I hope that I could answer the question regarding the speed up of our VASP calculations, and this video would be helpful for you. Please comment here or email to me your feedback and your question, and I will try to answer them. Please subscribe to this channel and hit the bell icon to be notified the next videos, and thank you again very much for listening.